this video, we're going to talk about net change as the integral of rate. As you can see, this looks a lot like exactly what we were talking about with the fundamental theorem of calculus part 1, and that's because it is exactly. We're just going to look at some real-world examples of the application of the fundamental theorem of calculus part 1. Which, recall, it says, although this notation is a little different, that the integral or area under a derivative function will be equal to the net change of the antiderivative function, or quantity being measured by some function s of t. So that quantity could be total distance, or total number of gallons, or total number of people. But let's say instead we're given just the rate, that we can compute an integral over that rate to find the total net change in the quantity. Let's look at a specific example to see a little more clearly what we're talking about. So let's say that the traffic flow along the function g of t equals 300 plus 200t minus 30t squared, where t equals 0 is 8 o'clock a.m. And we want to know how many cars pass from 8 till 10 a.m. In this problem, traffic flow is a rate. Because we're thinking of that as cars per hour in this case. And so if we want to sum up the total number of cars, notice that this t is constantly changing. The t is a continuous function. We can't just look at the number of cars at t equals 0 and t equals 1, because over the course of the hour, this rate is changing because the cars is continually changing. So using the fundamental theorem of calculus, in order to compute the total net change, we're going to have to take the integral from 8 a.m. to 10 a.m. And in the problem, we see that t equals 0 is 8 a.m. So t equals 0 corresponds to the time 8 a.m. And then we want to know 2 hours later at 10 a.m. So that's when t equals 2 a.m. And we're integrating over this traffic flow function. 300 plus 200t minus 30t squared d. This will give me the net and total number of cars. So to integrate this, let's find an antiderivative of this rate function, which will be 300t plus 1/2 of 200t squared. I'm raising the exponent, dividing by 1/2, minus raising the exponent becomes third times 30t cubed. So this is an antiderivative of this rate function, and I want to evaluate it as t goes from 0 to 2. The top bound is 2, the bottom bound is 0. This simplifies quite a bit, and I'll write out some of that simplification. This becomes 300 times 2 plus 1/2 of 200 is 100 times 2 squared minus 1/3 of 30 becomes just 10 times 2 cubed. This is evaluating along the top bound, and then I need to subtract out evaluating at 0. But notice there's a 0 in each one of these terms. This is 0 plus 0. I'm not even bothering in the 0 into each of these. I see that they all zero out because they're all multiplied by t, which is 0. And we see that the total number of cars in this case is 300 times 2, which is 600, plus 400 minus 4 squared, or 2 squared is 4, minus 10 is 40. So that's 960 cars. So 960 cars total are passing by in this 2-hour interval. So this is just an application of the fundamental theorem of calculus. I'm given a rate function, and I am asked to integrate to be able to find the total quantity of cars. Let's look at this graphically instead of algebraically. So suppose, here I got this off the internet, so of course it's totally valid. This is the net migration in the country of New Zealand, and these are in thousands of people. So this is indicating that in one particular year, this is the number of thousands of people that have migrated, the rate of migration per year. And for example, we could ask a number of questions. One question that I might ask is, how many total people migrated to New Zealand in the 50s? So because this is a rate function, and maybe I'll call this function t, my total net change in population will be given as the integral of this r of t function, dt, my rate population change. And in the 1950s, I'm looking from 1950 as my starting year, and I'm looking at 1960 as my ending year, and I could estimate the net change in people by finding an estimation of the area under this curve in this time period. And of course, because this is real world data, I don't have an exact value for any of these, but as an estimation, I'm going to say that overall, if I were to average out the areas, I would think that the value would be close to 10 times 7, so maybe I'll write is about equal to the area under this curve, which I'm saying is about 70, and in this case 70,000 people. And again, that's just an estimation based on this graph. But other questions that you can ask, what decades saw greater emigration than immigration? So these are decades where more people are leaving the country than are entering the country. And you can see people leaving the country would be indicated by a negative migration rate, that they're migrating out of the nation. And the only decade that I see, maybe from 1975 to 1985, we see a period of which more people are leaving than are entering the country. And if you shifted that, you could say it also looks like through the 1980s, we could argue that the area under this curve is greater than the area above the curve. And so I could estimate that in the 1980s, more people are leaving New Zealand than are entering New Zealand. So this is a way to graphically analyze this net change as the net change as the integral of a rate. The final classic example that I want to talk about is velocity. These are two variables that we've talked about a lot in this class. They come up in a lot of natural sciences. The relationship between distance and velocity, and we've already talked about how the integral of a velocity is going to give us our net change in distance. So suppose we have a projectile and its initial velocity is 100 meters per second. And we use this equation, which is one of Galileo's equations for velocity, to determine the total distance traveled. So in this case, our velocity curve is our rate, and we want to know how far does it travel in the first 15 seconds. So we're going to sum up the velocity as t goes from 0 to 15. Our function in this case is 100 minus 9.8 t dt. So to find the total, this is a rate. Velocity is distance over time. Well, it's the absolute directional distance over time. And to find the total distance, I'm going to find the antiderivative of this velocity function, which in this case is going to be 100t minus 1/2 of 9.8, maybe I'll write that, 1/2 of 9.8 t squared plus c, but I don't have to worry about that because I'm evaluating it as a net change as t goes from 0 to 15. So this ends up being 100 times 15 minus 1/2 of 9.8 is 4 times 15. This is evaluated at the upper bound, and you can see in your head that evaluating it at the lower bound will also just be a bunch of zeros because there's a t in each term of this integration. So it means that my total distance traveled in this case is going to be 1500 minus 4.9 times 15,